Hi everyone, Kalyan Kumar this side, and welcome to another episode of Quantum Mechanics. We're dealing with atomic structure. This is part 12 of atomic structure. You can check out the previous videos that I made for atomic structure, and I'll put the link of all of those videos in the description below. This is Quantum Mechanics 12D. We've done three parts A, B, C. A is the part where we introduced what is a wave equation. And these were beginners who are in grade 11, who have not studied waves so far. So the A part was an introduction to waves. What do you mean by a wave function? And time dependent, time independent wave functions. In 12b, for the first time, we talked about quantum mechanics in the form of Schrodinger wave equation. And in this one, we talked about how we can use the wave equation we derived in 12a, and using that, we can get the Schrodinger wave equation, both time independent and time dependent equations. In 12c, we talked about the understanding of fundamentals of Schrodinger wave equation. What does it imply? We talked about the particle in a box, which helped us apply the Schrodinger wave equation to simple situations, and that was a way of basically understanding what a Schrodinger wave equation stands for. Now, in this episode 12D, we are going to talk about the probability, the probability density, the radial probability density, the radial probability function. We are going to talk about probability in general, what the probability of an electron means, and what are the various types of probabilities we can get. And then we'll talk about quantum numbers. And with that, let's begin 12D, which is the radial probability distribution, radial probability function, and quantum numbers. All right, so here we go. The first one we're going to talk about is the radial probability function, or RPF. Now, you see, when you want to calculate the probability of an electron, and we have discussed that in the previous episodes, we used to say it is if psi represents the wave function, psi square or psi star is what generally gives the probability. But we have developed further into this, and we've been able to figure out what are the various types of probability. And when I say what are the various types of probability, meaning what is the probability of finding an electron at a given point? What is the probability of finding the electron at a given point at a particular distance from the nucleus? What is the probability of finding the electron at a certain distance from the nucleus in a thin spherical shell? What is the probability of finding the electron from the nucleus at a certain distance in a thin spherical shell of uniform thickness and unit thickness? So we'll figure out all of these. So radial probability function, RPF. So what I'm going to do is let us try to find the probability of finding the electron in a thin spherical shell. And this is how the shell is created. Now look at this. This is the sphere. Now if you look at the dark blue region, now imagine that you join these two parts, you'll get a sphere, as you can see. And imagine that you join these two parts, you will get a smaller sphere inside the big sphere. So the dark blue is the outer shell, outer sphere, and the light blue is the inner sphere. And we are trying to find the probability of electron in this region, thin spherical shell. So if I were to remove the volume of the smaller one from the bigger one, I'll be only left with this shell, this part, the darkest part. So let's figure out. Now we are assuming the radius of the smaller sphere to be r, and this is the center of both the spheres, and this is the distance of the larger sphere, which I'm taking as r plus dr, where dr is this thickness, this part. So what I'm going to do is I'm going to find the volume of the largest sphere, which will be 4 by 3 pi r plus dr the whole cube. Makes sense. Volume of the smallest sphere, which is 4 by 3 r cube. And the shell will obviously be the difference of these two. So volume of the spherical shell will be 4 by 3 pi r plus dr the whole cube minus 4 by 3 pi r cube, which results in this. You see, I expand this. So I get r cube and dr cube, then I get 3r dr into r plus dr. And here I get the r cube, 4 by 3 pi is common outside. So r cube gets cancelled. And now let's see what else gets cancelled. Now this I'm taking as, now dr cube I'm taking, I'm just ignoring this because it's going to be very small. And this dr into dr square also I'm ignoring. So I'm only having 3r dr into r, which is 3r square dr. And if I were to multiply this, this is the volume of the thin spherical shell. So the radial probability density of an electron at a point in space in an atom is given by the simple psi star, psi star, psi square. So at any given point, if you want to calculate the probability of finding the electron at any given point, it will be psi star. And since most often it will have some imaginary part, it will be psi star. Doesn't have an imaginary part, psi star generally becomes psi square. So this is the probability density of an electron at any given point in space. Then the radial probability density of an electron at a distance dr from the nucleus is going to be psi star dr. So if you want to calculate it at a particular distance from the nucleus, multiply by that dr. And what happens if you want to calculate this in the thin spherical shell? Well, you multiply by dV. The radial probability density of an electron in a spherical shell of volume dV is given by psi star dV, which is psi star 4 pi r square dr. Remember, whenever I'm writing psi square, I actually mean psi star if there is an imaginary function. So the radial probability distribution, which is the radial probability function in a spherical shell of unit length thickness, is given by psi star pi r square. And because, see, what is happening is the connection between these two is, I'm taking dr to be 1 of unit length thickness. So the radial probability function, which is psi star 4 pi r square dr, if I want to calculate per unit thickness, it will be called radial probability distribution. So it will be simply psi star 4 pi r square. Now it's known that even though we are comfortable with Cartesian coordinates x, y and z, it becomes much more easier to solve the Schrodinger wave equation if you were to convert the Cartesian coordinates into polar coordinates. They are called polar spherical coordinates. They're called r, theta and phi. So let's try to convert a Cartesian coordinate of an electron into its corresponding polar coordinate. So we are going to look at polar coordinates. Now solving the Schrodinger equation becomes complicated when we use Cartesian coordinates. And to resolve this, we use spherical polar coordinates. As the atom is spherical and the electron is moving spherically in 3D space rather than moving in planar orbits. So remember, the electron is in 3D environment. Don't think of that Bohr thing where you assume the electron to be moving in a circle. Now it is in a 3-dimensional. So we need something that will help in 3-dimension, and in solving differential equations, it becomes much more easier if you were to convert them into polar coordinates than using the Cartesian coordinates. So let's do that. Let's do the conversion. Now let's first convert the coordinates of an electron in Cartesian system to spherical polar system. So here I'm assuming P is the point in space in Cartesian coordinate system with coordinates x, y, z and O be the origin. So assume a Cartesian coordinate system. And let P be the location of the electron at any given point in time. And let us assume its coordinates are x, y, and z in the Cartesian system. We are going to convert this into its polar coordinate. And this is how we define those polar coordinates. So x-axis, y-axis, and z-axis. P is the point, x, y, z, and O is the origin. Let the radial distance of the point P from the origin be r. So from this point to this point P, let the distance be r. Now let's assume that the angle that r makes, that means this particular line makes with the z-axis P theta. So let theta be the angle between r and the z-axis. So this is how theta is defined. If somebody were to ask you, what does theta in the spherical coordinates represent? Well, it is the radial distance of the electron, is the angle between the radial distance of the electron from the nucleus to the z-axis is theta. And then let Q be the projection of point P on the xy plane. So remember, this is the xy plane, okay? This is the xy plane. This entire region is the xy plane. So I project this. So when I say project this, draw perpendicular. And this point is supposed to be Q. So I draw this line and this is Q. Now QR is the perpendicular from Q to the x-axis. So QR is the perpendicular drawn from Q to the x-axis. So let's draw this perpendicular meeting at R. This is perpendicular to the x-axis. And let us join the origin with Q, O and Q. So line OQ joins the point Q to the origin. Now the next thing that we represent, remember we've already got two of these spherical coordinates, R and theta. Now let's understand what is phi. Phi is this angle. This is phi. Angle QOR is phi. So this is the third spherical coordinate. Of course, the spherical coordinates of P are not R theta phi. They will be in terms of R theta and phi. So now what I'm going to do, so what is phi by the way? Phi is the angle between the x-axis and the line joining the origin to the projection of P in the xy plane. So Q, which is the projection of P on the xy plane, the line, the line joining this Q with the origin and the x-axis is phi. I'm going to join the z-axis with P. I'm going to draw a perpendicular. And then I'm going to draw a perpendicular from Q to y-axis. Now you will notice that let the x-intercept, that means OR be A. Let the intercept of y-axis O and whatever this point is, let's call it B. And O and whatever is this point, let's call it C. So let the x-intercept be A, Y be B, Z be C. So this is A, this is B, and this is C. So I have to get the values of A, B, C. And that will give me the conversion of Cartesian coordinates into spherical coordinates. So what do you think would be, if this is R and this is theta, isn't this the opposite side? So don't you think the opposite side upon hypotenuse, which is R, should be sine theta? So opposite side, which is ZP, let's say ZP upon R to be sine theta. So what will be ZP? Wouldn't it be R sine theta? So this is R sine theta. So by that logic, what will be this distance? Don't you think it will be r cos theta? So it will be r cos theta, right? It will be r cos theta because this is the base. So OZ upon r will be cos theta. And OZ will be r cos theta. So I got my C. Now what I'm going to do is, now you may wonder, why did I get this? Because this would be equal to this. So this bottom is also r sin theta. And why do I need this? I need this to get B. Okay. And I need this to get my A also. So how am I going to do that? Simple. Remember, if this angle is phi, this angle is also phi, because this line and this line, they are parallel. And this red line, this is the transversal. And the alternate angles are equal. So this angle is also phi. Now just try to understand. If this is phi, what do you think would be B? Now for phi, B is the opposite angle, right? So B upon the hypotenuse, which is r sin theta, should be equal to sin phi, right? Because sin phi will be opposite side B upon the hypotenuse r sin theta. So what is B? B is r sin theta sin phi. So B is r sin theta sin phi. By that logic, what will be A? Now A, remember, is the base. Base upon hypotenuse is cos phi. So A upon r sin theta would be cos phi. So what do you think A would be? A would be r sin theta cos phi. So this is how we convert the spherical coordinates, the Cartesian coordinates, into the corresponding spherical coordinate. Now that we have got this, now the wave function slightly changes. Remember, the wave function was based on x, y, z. We said psi x, y, z. Now we are going to call it as a combination of three wave functions. The wave function psi of an electron is now made up of three wave functions, one containing the r terms, one containing the theta terms, one containing the phi terms. And they can be intermixed also. So this way we can convert the wave function of the Cartesian coordinate system to psi equals r of r. This is the function that uses r, this is the function that uses theta, this is the function that uses phi. So in terms of polar coordinates, now the same radial things, the radial probability distribution, the radial probability density, the radial probability density at a particular dr, the radial probability density at dv, the radial probability function, the radial probability distribution, all of that we can get now in terms of r of r. And let's see how do we do that. So the radial probability density at a point, instead of psi square, becomes r of r square. And since it is radial, it will only contain the r terms. The radial probability density at dr would be rr square dr. The radial probability function of a thin spherical shell will be rr square dv, which is rr square 4 pi r square dr. And the radial probability distribution, which is the per unit length thickness, will be rr square 4 pi r square. Now with that done, let's look at quantum numbers. Now quantum numbers are basically some constants, some values that we get. And if you remember the last video where we discussed the application of Schrodinger wave equation to a one-dimensional box, we got something called n, and we realized that n can only take certain values. Similarly, after solving these Schrodinger wave equations, we were able to get three quantum numbers, three values that can only take certain specific values. So let's have a look. After converting the wave function into polar coordinate system and solving the resulting equation, we get three values denoted by n, l, and m. On solving R of R, we get N and L, while on solving theta of theta, we get L and M, while on solving phi, we get only M. N is called the principal quantum number, L is called the azimuthal quantum number, while M is called the magnetic quantum number. So let's quickly go through each of them. Principal quantum number N. Now N describes the distance that the electron is present in from the nucleus. So it not only talks about distance, it also talks about its energy. So N describes the distance of the electron from the nucleus as well as its energy. And as we know, this is the same N that Bohr had given, and it can only take natural numbers 1, 2, 3, etc. And if you remember the Bohr's theory, N equal to 1 is called K shell, the first shell, while N is equal to 2 represents the L shell, and so on. And this quantum number, as we know, was given by Niels Bohr in his theory. Now, theoretically, the value of N can take any value. You remember, we used to take even infinity in the case of hydrogen. But among known elements, the maximum value of N you will ever have in an atom is not more than 7. 7 is the maximum value. So, theoretically, the value of N can range from 1 to infinity, but for known elements, it does not go beyond 7. And higher value of N, higher is the radius of the shell as well as energy. We know this. And we also know, according to Bohr's theory, the angular momentum associated with an orbit or the orbit angular momentum is given by L equals nh by 2 pi. Remember, we are going to study a lot of angular momentum. We're going to talk about orbit angular momentum, and then we'll talk about some other angular momentum. So remember, this is the angular momentum due to its movement around the nucleus in an orbit. The maximum number of electrons in a given shell cannot exceed 2n square. Let's look at the azimuthal quantum number. Now, azimuth is basically a way of finding distance of an object through the measurement of angles. I'm not going into the depth of that, but basically we use it for stars. As they move across the sky, we can use angles to describe distances moved. So without elaborating in detail, azimuth is the direction of an object measured in terms of the angular distance. It represents subshells and their shapes. Now this is where things will get a little difficult to imagine. And remember, you can't imagine anyway, as I said. Quantum mechanics is not for imagination, it's not for intuitiveness, it's basically mathematical. But still, we would like to have a bit of a visualization to make it easier. So I'm going to give you a picture. Remember, this picture is a wrong picture. But this will help you sort of figure out what I actually mean when I say shell and subshell. So imagine the rings of Saturn. Imagine Saturn is the nucleus. Despite Saturn being very big, let's assume it's a small point. That's the nucleus. And the rings around it are the ones which contain shells and subshells. So imagine there is shells, thick lines around the nucleus. So there are thick lines. Each of these thick lines are, if you magnify them, they're all made up of some more circles. So the thick circle, the thick shell, despite the fact that I'm trying to give you a two-dimensional view, but just bear with me. So it's a circle, a thick circle around the nucleus, and the thickness is made up of several layers of circles. These are called subshells. The shell contains a lot of closely packed circles, and they are called subshells. Now, of course, here we're also going to talk about the shape of subshells. And right now you're going to say, okay, the image that you gave me is circular. No, it's not. This is just for the sake of understanding of what a subshell can be visualized. And again, it's not a true visualization because you simply cannot visualize these things. This is just to give you a bit of an ease in digesting the principal quantum number, the shell and the subshell. Now, it represents subshells and their shapes. For a given value of n, there are n values of L. So if n is 4, there will be 4 values of L. If n is 2, there will be 2 values of L. The lowest value of L is 0. and this was given by Sommerfeld. Therefore, for a given value of n, the values of L range from 0 to n minus 1. Now, the values of L with an increment of 1, it starts from 0 and goes up to n minus 1, meaning there are n values of L. See, 1 to n minus 1 are n minus 1 values. 0 to n minus 1 is n values of the L. Therefore, L has totally n values starting from 0 going up to n minus 1 with an increment of 1. So, L equal to 0 refers to S subshell. So, the subshell is given a name S. When L is 1, it is given the name P subshell. When L is 2, it's given a name D subshell. L is 3, it's given a name F subshell. And here I have a table that helps you figure out how to get N and L. So for N equal to 1, you can only have one value of L, which is 0. Because remember, the number of L values has to be equal to the number of N value. And the lowest value of L is 0. It will always start from 0. This is denoted as 1s. When N is 2, L can take two values, 0 and 1. Because remember, it can go from 0 to N minus 1. And when L is 0, we call it 2s. When L is 1, we call it 2p, because L equal to 1 is p. When N equal to 3, you get 0, 1 and 2. You have 3s, 3p, 3d. When it is 4, okay, you have these many values, 4s, 4d, 4p, 4f. And we don't have to talk about 4g, etc. because none of the known elements have that. Now, for a given value of N, the energy of subshell increases with increases in the value of L. Now, for elements other than hydrogen, remember this is very important. For elements other than hydrogen, for a given value of N, you have various values of L. Remember, if N is 4, there are 4 values of L. 0, 1, 2, 3. So the 0 subshell will have lower energy than the 1 subshell, L equal to 1. L equal to 1 will have lower energy than L equal to 2. L equal to 2 will have lower energy than L equal to 3. Meaning S will have lower energy than P, P will have lower energy than D, D will have lower energy than F for a given value of N. For a given value of L, the energy increases with increasing value of N. So if you fix L and change N, well, as N increases, energy will increase as expected. So 1s is less than 2s, 2s is less than 3s, 3s is less than 4s. Same goes for P, same goes for D. Now, in a subshell, an electron has another angular momentum called orbital angular momentum. Though I have not introduced the word orbital, which I will introduce when I talk about M. We talk about orbital angular momentum. And this angular momentum is different from the orbit angular momentum, because this thing depends on L value. So the orbital angular momentum L is given by L equals, the angular momentum L is given by root of L into L plus 1 H cross or H bar, which is H by 2 pi. Now, orbit angular momentum of electron is the angular momentum of an electron around the nucleus of the atom, while the orbital angular momentum of an electron is its angular momentum about the center of the orbital, which is dependent on the shape of the orbital itself. So, the orbital angular momentum depends on the shape of the subshell, which is why it is depending on the value of L. Now, the minimum number of electrons in a given subshell will be 2 into 2L plus 1. Now, let's look at the shapes of subshells. Now, S subshell is spherical in shape. Now, what this means is, it doesn't mean the electron is moving in a sphere. These are the regions of high electron density. That means if you say that an electron is in 1s, it means the sphere in first shell with L equal to 0 has the electrons probability. When the electrons probability is plotted, or we say, where all can the electron be? Give me the region of space where the probability of finding the electron is very high. And if I say, okay, this is the region, that region it becomes a sphere. So that is why we say S subshell is spherical. Now don't imagine the picture that I showed you of Saturn, because now you will say, okay, you said subshells are those tiny circles. How do you fit a sphere in that? No, that was just for understanding shell and subshell. Now you're going to figure out the shape of subshells. So because this is not an intuitive thing, quantum mechanics is always quantitative, not qualitative, even though we are trying to do things qualitatively. While the P subshell is supposed to be dumbbell in shape, and the D subshell is supposed to be a double dumbbell, and the F subshell does not have any particular shape, and it is very complicated, and we don't have to talk about that. Then comes the third quantum number, the magnetic quantum number. This was given by Zeeman due to Zeeman effect, when there was splitting of absorption and emission lines in a magnetic field. This determines the orientation of subshells. So remember, the subshell L can have various orientations. For example, I showed you a dumbbell, right? But in which direction did I show you the dumbbell? I showed you the dumbbell up and down. Does it mean it can only be up and down? No, it can have many orientations. A sphere, on the other hand, can only have one orientation. It doesn't have an orientation. It is spherically symmetrical in all directions. So for S subshell, there is only one orientation, which is that itself. Whereas in the case of other subshells, which are probably oriented in a particular way, there you can have multiple orientations. So M denotes these orientations. The number of M tells you the number of different orientations, not the value of M, the number of values of M. So M has only one value, it means it has only one orientation. If M has 3 values, it means it has 3 orientations. If M has 5 values, it means it has got 5 variations, 5 particular orientations. So each subshell can have a certain number of fixed orientation, and each of these orientation is called an orbital. The number of M values determines the number of orbitals in a subshell. For given value of L, there are 2L plus 1 values of M. So remember, for a given value of L, you will have maximum 2L plus 1 values. And how will these values change? The value of M will go from minus L to plus L with an increment of 1. So if you have 3L, L is 3, you have minus 3, you got minus 2, you got minus 1, you got 0, you got 1, you got 2, you got 3. So minus L to plus L with an increment of 1. So the values of M range from plus L to minus L through 0 with an increment of 1, and these are the values of L. L0, M can only have value 0. L is 1, L can have 3 values. L is 2, L will have 5 values. 3, it will have 7 values. For the S subshell, there is only one value of M, as there is no orientation available. For P subshell, there are 3 values of M, as it can be oriented in the 3 axes, which are Px, Py and Pz. So these dumbbell orbitals are oriented in the 3 axes, namely x, y, z. So you have x, y and z. You have the Pz, this is Px and this is Py. M equal to 0 denotes the Pz by default, while Px and Py can take any values of minus 1 and plus 1. So when it comes to P, remember, we assume by default Z axis to be the principal axis for us, and the lowest values of M are reserved for orbitals having Z in them. So Pz is M equal to 0, whereas Px and Py can take plus minus 1. Anyone can take plus 1, anyone can be given minus 1. For D subshell, there are 5 values of M, and this implies that D subshell has 5 orbitals. Since 5 orbitals determine orientation, the 5 orbitals are denoted by dxy, dyz, dxz, dxy minus y squared, dz squared. So let me show you each of these. dxy, xz and yz are oriented in the xy, xz and yz plane respectively in between the axes. So if this is x, y and z, the xy will be in the xy plane, which will be this or horizontal plane. So the blue, let's say, represent plus, then the red will denote minus. Remember, this is the sign of the wave function, which has no physical meaning. Then, if you want to know dyz, this is yz. Yz, remember, will be in this plane. And dxz, xz will be in this plane. And then dz square is a little unique. It has one lobe in the z axis, while there is a donut shaped lobe, which is the minus value in the xy plane. Now, for m values, m equal to 0 denotes dz square. Plus 1, minus 1 are the ones which have z in them, yz and xz. Plus 2, minus 2 are the ones which don't have z in them, which is x square minus y square and xy. And then we come to the last quantum number, s. And remember, this quantum number is not given in the Schrodinger wave equation. It does give you only n, m, and n, l, and m. The s quantum number is given separately, and so this is not a part of the Schrodinger wave equation solution. Now, this is given by Goldschmidt. It describes the spin angular momentum of an electron. So now we have one more thing. We are saying electron also spins clockwise or anti-clockwise. And one of them by default is given plus half, the other is given as minus half. There are two values of s possible, plus half and minus half, fixed values. For one given value of m, you can have two values of s, plus half and minus half. An electron spins around an axis and has both spin angular momentum and orbital angular momentum. Because angular momentum is a vector, the spin quantum number has both magnitude plus and minus half. And spin angular momentum is given by s into s plus 1 h bar. And each m value can have two values of s, as I said. Now remember, there are three angular momentums that we have talked about. Orbit, nh by 2 pi. Orbital, root of L into L plus 1 h bar. And now the spin. This is due to the movement of the electron around its axis. Orbital is due to the movement of the electron at the center of its orbital. And orbit is the one that is moving around the nucleus. So it has got three angular momentum. And remember, as much as you try to imagine this and try to create an image in your mind, it won't work. Don't waste your time on that. You just have to know how to use these, when to use this. And at the end of this lesson, we'll also do a couple of questions. Some tricky questions which can help you understand how these are applied. So with that, we come to the end of this video. Watch this video as many times as you need. And if you have any questions, anything that you're not clear at, please put them in the comment section below. And with that, this is Kalyan Kumar signing off. Have a great and wonderful day. Thank you for watching, and I'll catch you in the next one.